Alright, so here is a problem, and it says that we have a 25 kilogram box, and we're pulling it with an applied force of 60 newtons, which is going to be at an angle of 30 degrees above the horizontal, and we want to find the acceleration of that box given the fact that mu sub k, the coefficient of kinetic friction, equals 0.15. So if I draw the picture of it, this is 25 kilograms, and there's a rope or something, handle, tied to it, and the handle's going at 30 degrees above the horizontal. So this is my force applied, which equals 60 newtons, and this is my 30-degree angle. So if I were to do the free body diagram, which I always have to do, I'll try to find all the other forces that I can. The first thing I will do is break this down into its x and y components. So instead of talking about pulling on this box to the right and up, I'll actually find the pulling force to the right and the pulling force up. So if I have the hypotenuse and an angle, I can find the adjacent side by saying the hypotenuse times the cosine of the angle. So this force sub x would be 60 newtons times the cosine of 30 degrees. And this force sub y would be 60 newtons times the sine of 30 degrees. So when I do those on my calculator, they come out to be some numbers. This is 51.96. And over here, this is 30. So those are the first steps we should do. Anytime you see a vector, not along the x or along the y, if it's somewhere in the middle between them, break it apart into its x and y components. Another force that I would like to put on here is the weight. So I go to the center of the box and I go straight down, and the weight equals the mass times gravity, which is 25 kilograms times 9.8 meters per second squared, and that's going to come out to be 245. Okay. Now, the next one that I'm going to look at is going to be the normal force. And the normal force is a difficult one most of the time. The normal force is going to be here. So the normal force is going to be going this way. So you see, the normal force has to be perpendicular to the surface. So, the normal force would be the perpendicular force that the object is sliding along a surface, the box is pushing on the floor is pushing back on the box, and that's the normal force. The floor pushing back along the box. So the normal force is perpendicular to the ground. Okay, but what is the normal force? Well, the weight of this box is 245 newtons. Okay, but the normal force is how heavy does the box feel to the ground. This is something that's happening to the box in the vertical direction. Someone is pulling on this rope, and what they're doing with the rope is they're pulling up. So they're not just pulling the box to the right, they're pulling up on it a little bit. So by pulling up on it, they're pulling up on it by 30 newtons. They actually make the box feel lighter to the ground by 30 newtons. So the normal force is not just equal to the weight, it's equal to the weight and how this is interacting with the weight. So the weight is going down, and this is going up. So we're going to subtract them. If you take 245 and you minus away 30, you will get 215 newtons. So that is going to be the normal force for this particular box. And once you have the normal force, then you can go and find the force of friction. So the force of friction is just going to be a formula, and the force of friction, and we're talking about, in this case, kinetic, is equal to mu, in this case, subscript k, times the force normal. We were told what the force of kinetic friction was. So, the coefficient of kinetic friction. So it's 0.15, and we're going to multiply it by the force of the normal, 215. And that is going to end up coming out to be 32.25. So that is our force of friction. So our force of friction is over here. It's where the two surfaces are coming into contact with each other. There's a force of friction of 32.25 newtons. Okay. So we have all those numbers. I would like to erase all of this and show you the numbers a little bit clearer. If you can see this drawing, I've drawn something called a free body diagram. That's its name. And the free body diagram shows all the forces acting on this box. So what I've done is, I've shown you the weight very clearly. I haven't shown you very clearly the applied force, because the applied force was a rope going in two directions. I've broken it down into two separate forces. So the rope was pulling to the right with 51.96 newtons, and the rope was pulling up with 30 newtons. Also, we calculated a moment ago the normal force, so I have the normal force here, 215, and I also have the force of friction, 32.25 newtons. So now what I can do is with this, I can cancel off any force that is the same going up and going down. So what I notice is I have 215 going up, and I have an additional 30 going up. If I add those two together, I will get 245 going up. They'll cancel out this 245 going down. So I only have these two forces left. I could redraw that, and I could say I have a simpler free body diagram, and with my simpler free body diagram, I could say I have a force going to the right of 51.96 newtons, and that would be my force in the x direction, and I have a force going to the left of friction, and that would be my 32.25 newtons. And I could look at this, that's a 2, and I could look at this and I could say, well, I can add these two vectors together. I could say the sum of all the forces would be a positive 51.96 newtons plus the negative 32.25 newtons. And when I do that, I could come up with a number, and the number would end up being 19.71. So I could draw another free body diagram, the most simple one, and I could show the box on it, which is 25 kilograms, and I could show the net force. So the sum of all these forces is 19.71 newtons. And if I just zoomed in here, then that's what I see as my net force. So my net force is now known. And if you look in this diagram, the last one, all I have is one force and one mass. So the question is, how do we get the acceleration? Well, the acceleration rate is, it's the sum of all the forces over the mass. So in this case, it's going to be 19.71 newtons divided by 25 kilograms, and that is going to come out to be 0.788. So the acceleration is going to be 0.788 meters over a second squared. Okay. So that's my final answer right here. Okay. So we were given a problem with a force pulling, an applied force pulling an object along a certain angle, and we broke everything down to the x and y components, and we canceled out when we could, and we simplified where we could, and we came up with one force, the net force, acting with the mass, and we came up with an acceleration of 0.788. When I first started giving these talks, I had said that I would like to use the Cartesian coordinate system for the entire course. And possibly, hopefully I said, for most of the course, because there's one small piece in the course when I don't use Cartesian coordinates. So if you don't remember, Cartesian coordinates is when we look at this thing called the xy axis, and everything going that way would be positive x, and everything going upward would be positive y. And if it's going this way, we would call it negative x, and going this way down is negative y. So the only time I really don't want to use that is with something called an inclined plane. So an inclined plane is a hill, it's a ramp, and occasionally we have kids sliding down hills. We have somebody who's on a roof, which is slanted at a certain pitch. We have cars trying to drive up hills, and we need to deal with inclined planes. So an inclined plane is basically something like this. So I'll try to draw a relatively small angle inclined plane. Okay, so that's my inclined plane. It's relatively small, and small angle. That would be theta. And if I put something on it like a box, this would have a certain amount of mass, and I'll just call it M for mass. And what I've asked people to do since Chapter 4 with forces, I would say try to draw all the forces you can. So in this particular case, there are some forces. One of the forces would be weight, and the weight's going straight down to the center of the Earth, which is equal to M times G. Okay. So for a moment, I want us to stop, and I want to say, if you're looking at your piece of paper, you could take your piece of paper and you could skew your piece of paper probably this way. So if you had your paper like this and you turn it this way, just for a moment, I want you to see what's happening. So I'm trying to have you turn it in such a way that your ramp will be a horizontal. This part of the ramp, you know, the surface of the ramp will now be a horizontal line that you're looking at. So if I draw that, you might see is this. So we're almost out of range, but it all fit. So you see, if I take this picture, which you've drawn possibly in your notes, and you draw it exactly like this, but now I'm asking you to take your piece of paper, and so where you've just had your notebook this way, say, and you drew that, now I'm asking you to turn your notebook page a little bit like this, and what you'd be looking at is, you'd be looking in this. You'd be seeing that there's a flat surface, and you'd be seeing this force vector that's coming down here at an angle. Okay, so if we now go and say the Cartesian coordinates, remember the Cartesian coordinates? We always had going to the right, so we would say going to the right like this would be positive x, and then we would say going vertically upward would be positive y. Okay, and then in the same case, going down would be negative y, and going to the left would be negative x. So that's the Cartesian coordinate system. And then you see this particular vector called the weight is not pointing along any one of these axis lines for x and y. So we have to, which two ways would it be pointing, you might say? I might say that this is pointing towards the positive x direction, and it's also pointing towards the negative y direction. So I want to take this and I want to break it up into two completely different vectors. So what I want to do is I want to say it's coming down and it's going over. Okay, and in this case, if this is a small angle and I drew it really, really well, this would be the exact same small angle. So this here would be 30 degrees, or theta. Okay, so, and the hypotenuse would be this thing called the weight. So this right here would be the weight, mass times gravity. Okay, so that's what the weight vector is, mass times gravity. So if you would just now look at this, if this is an angle, then this piece over here is called the opposite side, and there's a formula. The opposite side is equal to the hypotenuse times the sine of the angle. And over here, this side would be called the adjacent side. This side is right next to the angle. So this is the adjacent side is called the hypotenuse times the cosine of the angle. Okay. So there's a lot of stuff that's happening right here. And all I'm doing here is showing you how I'm deriving these particular formulas. So if you look at this, the only two things I'm going to need you to take with you is this and this. And then I'm not even going to ask you to remember the word opposite, because it's really not pointing to the right. If you look at what this force is doing, this force is pointing parallel to the direction of the surface of that hill. So you see, if you put a sled on a hill, if you put a box on a slippery surface, if you try to park your car and the road is somewhat icy, there will be this thing that is going to be forcing you down the hill. And what it is it's a piece of the weight. So your car has a certain amount of weight. A piece of the weight will try to pull your car parallel to the hill down. Okay? And another piece of the weight will be trying to push your car perpendicular into the hill. Okay, so these two things are going to happen at the same time. So if I would just take two pieces of information from here and go back to the original drawing, I could say that there is a force trying to push something parallel down the hill, and I'll call this thing force parallel, which is mass times gravity times here, the sine of the angle. I have to erase a little bit of the other one here. And then over here, there's a little piece of the weight trying to pull the thing perpendicular. This orange line here was going perpendicular to the surface, so we'll call this one perpendicular to the surface. And this one here would be called the force perpendicular, which is equal to mass times gravity times the cosine of the angle. And with that said, I can get rid of this. So when I do inclined planes, and pretty much only when I do inclined planes, I decide that I don't want to use the old-fashioned Cartesian coordinate system, which always had going to the right as being a positive x, and going vertically upward as being a positive y. I'd like to change it, and I'd like to draw a new Cartesian coordinate system, so it's going to go like this. So it's getting crowded there. So if I show you again a hill, and I put a box on it or something, with some mass, I'd like to say this is going to be my new x direction, and this way would be my new y direction. Okay. So you see, I'm now looking at something from a different viewpoint. I'm looking at it as far as the top of the hill. I'm looking at it parallel to the top of the hill surface, and perpendicular to the hill surface. So this is the angle we're talking about right here. Okay. And I will not draw this particular thing. Weight is a true force, it's a true vector, and weight points towards the center of the earth. So I don't want to draw this weight. Actually, this is a piece of the weight, and this is another piece of the weight. So I'm only going to draw these two pieces of the weight because I've broken these things up into my new. Going this way is my x-axis. So I've taken the weight and drawn a piece of it going along the new x-axis, and I've taken the weight and I've drawn a piece of it going along the new y-axis. Okay, so just to do a quick sample problem. Let's say I have a 50 kilogram mass. So what I'm saying here is a sample problem. I have a 50 kilogram mass on a 20-degree hill. Whenever they talk about the angles of a hill, it's always with respect to the horizontal line. So I've shown it here, and I have this. They could say find the components of the weight. So I could say find components of the weight. Okay. Well, I don't want to just find the weight. Weight is a vector that's going straight down to the center of the earth. But when you're on a hill, the only two forces that should be drawn right away for the free body diagram would be the force going down the hill, and this is called force parallel, which is m times g times sine of the angle. So if I plug that in, it would be 50 kilograms times 9.8 times the sine of 20 degrees. And if I plug that into my calculator, it comes out to be 167.59. So this is coming out to be 167.59 newtons. Okay. And I could find the other one. What is the force going perpendicular into the hill? So I could find a piece of the weight going this way, and this one will be called force perpendicular. So that equals m times g times the cosine of the angle. I could plug that in. So the M is 50 kilograms, and the G is the number 9.8, and it's the cosine of 20 degrees. So if I plug that in to the thing, it's 50 times 9.8 times cosine 20 degrees. It comes out to be 460.5. So this is 460.5, and it's newtons. Okay. So that's the force parallel to the hill. Let me pause the tape and clean this up a little bit. I cleaned up the drawing a little bit, so you can see now we just have a box. It's on a hill. It has a certain mass. There's a piece of the weight pulling it straight down parallel to the surface of the hill. Here's a piece of the weight pulling it perpendicular into the hill. And these two vectors, when you add them up together using the rule of vectors, they will equal the weight of that particular box. So this is usually a surprising statement that a lot of students say, whoa, wait a minute. So for instance, what I'm saying to you is the weight of that box is just mass times gravity. So if I plug it in, 50 kilograms times 9.8 meters per second squared, that equals 490 newtons. And the words I just said to you is, if you take this particular vector and add it with this particular vector, you will get the total weight, because this is a piece of the weight and this is also a piece of the weight. So I'm asking you to think for a moment, how can you add this vector and that vector and come up with this particular number, 490? Because that is the true weight, and this is a component of the true weight. That's another component of the true weight. So think about that for a moment, possibly hit pause, and then see what you can come up with. Well, what you should have come up with is we can't just add vectors if they're perpendicular to each other. If there's two vectors pointing in the same direction, then you can add them up like numbers. And if there's two vectors pointing in opposite direction, then you have to subtract them, because we have to use the rules of vectors. But if you have two vectors that are perpendicular to each other, you can't just simply go and add them up. You have to add them up using something called the tip to the tail method. So if we use the tip to the tail method, what would come out of this is we can see this one's going down the hill a little bit. So if we go down the hill a little bit, and this is the number 167.59 newtons, and then this one is going perpendicular into the hill, so it's kind of going like this, and this one is 460.5 newtons. Well, the true weight would be if we went from the overall beginning to the overall ending. So if we did that thing tip to tail, then we would go from starting to ending. And this is going to be the true weight. So if you just, with your calculators, figure out this piece, which would be a squared plus b squared equals c squared, the a could be the 167.5, the b could be the 460.5. And if you did that, 167.59 newtons, square it, plus 460.5 newtons, square it, and then we have to set it equal to c squared, and then we have to take the square root of both sides. So let me do that. My calculator is coming out to C should be the number 490. And then it has a lot of decimal points. It's like 0.047 newtons. Okay, well, isn't 490 approximately equal to 490? I'd say they're the same. The reason for the decimal points is when I did the calculation, I didn't write every single exact number. I rounded a little bit. So it wasn't exactly 0.59, it was 0.589, I think. And over here, it wasn't exactly 0.5, it was 0.449, so I kind of rounded that to 0.5. Okay, so that's the way that these two vectors are in fact the weight. So whenever I'm on an inclined plane, I never ever draw the weight going straight down. Okay. So if we're looking at this box and we have the parallel force and the perpendicular force, usually there's a word problem that has questions involved with it. So this is a word problem that's evolving a long time with the time. Here's question A. Find the normal force on that particular box right over there. And then the second question is find the acceleration of the box. Okay, well, the normal force. The normal force by definition is the force that the surface is going to push back in a perpendicular fashion on the object. So if the box is pushing on the surface of the hill, then the surface of the hill has to push back perpendicular to the surface, and it has to push back on the object. So the normal force would be going this way, and that's the force normal. Okay, so if you look here, they're lining each other up. So we have the normal force, and we have this thing, and they're pointing in the exact same direction. They're both perpendicular to the surface, and if you look at them again, they should be equal and opposite. So this is pushing perpendicular into the hill with 460.5 newtons. This should be pointing out with 460.5 newtons. So that's your answer for question B. They said, what's the acceleration on this particular box? Pretend it's not a box. Pretend it's a sled. There's a wooden sled or a plastic sled with a kid in it, and they're going to slide down the hill. Well, when they sit on the hill, a piece of their weight pushes the sled perpendicular into the hill. But then the hill has to push back on the kid and the sled perpendicular. So these two forces are equal and opposite, and they'll cancel each other out. So if these two things here are canceling each other out, the only force that remains is this one. Okay? So as these two here cancel each other out, then this thing right here is called the net force. So if this is the net force, we have the sum of all these forces equals m times a. That is the net force. 167.59 newtons equals the mass of this sled, or whatever it is 50 kilograms. And we have to get a. So if we divide both sides, so we have 167.59 newtons equals 50 kilograms times a. Divide both sides by 50. And I get 3.35. So that's the acceleration rate. So you have some box on a hill and it's a slippery surface, and something is accelerating down at a rate of 3.35 meters per second squared. Okay, so that's our acceleration rate. This is a sample problem of a hill, an inclined plane, with friction, and instead of writing out the whole problem, I've given you the picture. So basically, the problem says there's a roller coaster that's going to reach the top of the steepest hill with a speed of 6 kilometers per hour. So I've written the initial speed is 6 kilometers per hour. And then it said it's going to descend the hill, which is at an average of a 45-degree angle. So I'm showing you the angle of this hill is 45 degrees, and it said that the length of that hill is 45 meters long. What is the speed going to be at the bottom of that hill? So you see, I'm looking for the final velocity. Even though I say velocity here, we're doing energy conservation, so it'll be a speed. We'll get the magnitude of the final velocity. That's the question mark. And it also said that the coefficient of kinetic friction would be 0.12. So we haven't talked about rolling friction, so let's just for a moment imagine that it's just sliding. Okay, so it doesn't make a lot of sense with a roller coaster car and wheels, but the way we'll do it is we'll just say it's sliding down this hill. So here I have the car at the beginning, here are the cars at the end. There's still people in it. I just noticed I forgot to draw people, but we still get the kids in it, or whatever, adults. And we just want to know the speed down here. So the first thing I would do is I would convert, and I would say that oh, they gave me one more piece. Did they give me more information? No. Okay, so the first thing I would do is I'd convert this. So the initial velocity, they say 6 kilometers per hour, but I have to convert that. So I'd say in 1 kilometer, we have 1,000 meters, and I'd also say in 1 hour, we have 3,600 seconds. So if you convert this, the initial velocity would be, I'll just plug it in. It comes out to be 1.67. So the initial velocity is 1.67 meters per second. And we also know that the length that they're going to go, so delta x, we'll call this our x direction going down. So delta x is going to be 45 meters, and we'll say the final velocity is unknown. So what we're essentially doing is we're looking for the acceleration, and we're using the chapter 4 formulas to help us find the acceleration. So right over here, let me just draw the surface of this hill. Okay, and let me say I have a cart on it and it has a mass. So the two formulas we need to know about inclined planes is there's a force called the parallel force, which is mass times gravity times the sine of the angle. Okay, and there's something else here called the perpendicular force, which is mass times gravity times the cosine of the angle. Okay, and the perpendicular force in this case is a piece of the weight. That's these two things that I've shown are the weight of it. If you add these two vectors together, you'll get the total weight. So I have a piece of the weight going down, perpendicular into the hill, so that must mean that the hill's going to push back on it with a force normal of m times g times cosine of the angle. Okay, and then over here, those are two forces, and then over here there's another force called the force of friction. So if the roller coaster is sliding and moving down the hill, there'll be a force going opposite up the hill. So the force of friction equals mu times k, mu sub k, times the normal force. And in this case, this is the normal force. The normal force is m times g times cosine of the angle. So I'll write that. This is m times g times cosine of the angle, because by definition the force of friction is mu times the normal force, and that is the normal force. Well, these two cancel out. The ones that are perpendicular to the hill are going to cancel out. So this and this are going to cancel out. Okay, and then we're going to say we have to somehow find the acceleration. So if I were to simplify this picture a little bit more, let me just move over here a bit. I'll go to this point. I'll say here's my hill, and I'll say here's my mass, and I'll say going this way we have m times g times the sine of the angle, and going this way we will say we have m times g times the cosine of the angle, and we will say we are moving down the hill, okay, because they told us this roller coaster is in fact going down the hill. And if you just think about your own experience in life with roller coasters, if you've been on them, then usually you go relatively slow at the top and you go faster, 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 faster as you're going down the hill. So this should be a bigger number. So we are going to be moving this way, but not only moving, we're going to be accelerating that way. So we're going to be accelerating this way. So I'll call going down the hill my positive direction. And then I'll say the sum of all of these forces is, well, let's just add them up. So we've got, well, let me say, the sum of all the forces is equal to, I'll call this, remember I said I'll call x the positive direction, the way the thing will move originally. In this particular case, this is the force of friction. I forgot to put this mu. So I still need this mu here. Okay, so this would be mu mg cosine of the angle, the force of friction. And this would be a piece of the weight pulling it down the hill, m times g times sine of the angle. And as I said, this is moving down the hill, this is accelerating down the hill, and when I have a new coordinate system, I let the positive x direction be the way it's going to move. So going this way will be the positive direction. So what I'll say is the sum of all these forces equals this one. So this would be m times g times sine of the angle, plus, because sum means add them all up, and I'm going to add this one. Now this is going in the opposite direction, so I'm going to say a negative. So I'm going to say plus a negative mu mg cosine of the angle. And another way to write the sum of all the forces is just to say ma. So I could take this away and say that's equal to m times a. So when I plug all this in, the m's cancel out, and I'm left with a. So the acceleration is equal to a. So gravity is the number 9.8. Sine of 45. Minus mu. Mu is the number 0.12. Okay, so if I just do that math out, this becomes 6.93 meters per second squared. And then I have to say minus 0.83. So when I combine them, it combines to be 6.1 meter per second squared. That's my acceleration. Okay. But I didn't want what I wasn't asked what is the acceleration. I was asked what is the final speed of this roller coaster car when it gets to the bottom. So the kids are up here, they're sliding down, there's a little bit of friction, it's slowing them down than it would have. If there was absolutely no friction, it would be a very, very big speed. So here's our acceleration rate. And using these things that we used from Chapter 2, if we have v initial, if we have delta x, if we have the final velocity, if we have the acceleration, we can plug those things into some formula from Chapter 2, and we can get what is the delta x. Okay. So now I have the acceleration. The acceleration I just found was 6.1 meters per second squared. I'll use a Chapter 2 formula, and the Chapter 2 formula uses the v final squared equals v initial squared plus 2a delta x. I'll plug in the values. I don't know the final velocity. I did know the initial velocity. That was a trick, by the way, in the problem. They gave it to you in kilometers per hour. If you didn't remember to change that, you were wrong from the get-go. Plus 2, a we just found is 6.1 meters per second squared. Delta x was 45 meters long as we went down this hill. So when I plug those things in, I got this piece and I got this piece. And when I add them together and then take a square root, I get 23.49. So it comes out to be 23.49 meters per second. And that would be the final answer up here. So that's something like 46 miles per hour. So those kids, I guess, are having somewhat fun.